Okay, so we are going to look at no load and block rotor test of an induction motor. In fact, last class I had started on no load test and I told you that no load test is very similar to the open circuit test of a transformer, whereas the block rotor test is very similar to the short circuit test of a transformer. So, this is because if you actually look at the equivalent circuit of the induction motor, I normally have R1 here, X1 here, then I have RC and this is going to be XM, and what I have as the rotor parameters, I am going to have this as R2 dash by S and X2 dash, and this is going to be essentially short circuited because the rotor is inherently short circuited. Here is where I am actually applying the value V1, that is the stator applied voltage per phase. If I am looking at the motor running freely, this slip will be close to 0. So, whenever I am actually running it freely or free running test, I am going to have S equal to 0, because of which it is as good as rotor is open circuited, because R2 by S becomes infinity, right, at S equal to 0. So, I am going to have R2 dash by S equal to infinity. So, I am going to have rotor open circuited. So, this is equivalent to open circuit test of an induction motor, open circuit test of a transformer, I mean. Okay. Whereas, if I am going to have short circuit, so if I am going to have essentially the block rotor condition, if the rotor is blocked, right, then in that case I am going to have S equal to 1. So, R2 dash by S becomes basically equal to R2 dash itself, which is very clearly the normal short circuit condition of the induction motor. So, it is equivalent to short circuit condition of the transformer as well. So, please realize that the no load test is corresponding to open circuit test of a transformer and block rotor test is equivalent to short circuit test of a transformer. Now, let us try to look at what is actually the connection that is made under open circuit condition. So, I am going to have actually this as one of the wattmeters, which is going to one of the phases of the induction motor. Let us say this is the induction motor stator. So, this is going to be a meter and this is coming through the wattmeter W1. I am going to use 2 wattmeter method clearly. This is the second phase of the induction motor and this is the third phase of the induction motor. The third phase will also be connected through another current coil of the wattmeter. This is the pressure coil. So, the pressure coils are getting connected together in one of the phases. So, I am going to have actually a 3-phase auto transformer sitting in between, so that I will be able to apply variable voltage if I want to. So, this is my 3-phase auto transformer and I am going to have essentially the 3-phase supply connected here. So, this is A, this is B and this is C. Similarly, these are the induction motor terminals A, B and C. Okay. Now, I am going to show the rotor as a squirrel cage rotor, which is somewhat like this. So, I have shown a squirrel cage rotor. Now, the ammeter measures whatever is the current I0, let us say, and I am going to measure the voltage here, line to line voltage, which is V0, and I am going to measure what is W1 and what is W2. So, I can actually mention the terminals here. This is M1, this is L1, this is common and this is V1. Similarly, this is going to be M2, this is going to be L2 and this is going to be common and this is going to be V2. This is how the terminals are. Now, I am going to note down the readings V0, I0 and W1 plus W2. Most of the times when I am not going to have the induction motor loaded, I am going to see that one of the wattmeters might kick back, that is I will have the needle of this wattmeter going below 0, in which case I have to reverse the current coil and note down the W1 as the magnitude whatever it is. Now, after the current coil is reversed, I will be able to note down the reading. Let me just note down the reading as W1, but the net power under this condition I have to note down as W2 minus W1, because I have reversed the current coil, I have to take this reading as negative. So, this will be the net power. So, let us say I have noted down after doing all that jugglery what is V0, what is I0 and what is W0. These I have noted down. Please note the no load current of the induction motor will be still as high as 30% of its rated current. So, I have to write W0 minus whatever is my I0 per phase, the whole square, multiplied by R1. R1 actually is my per phase resistance of the stator, multiplied by 3. This will give me the total copper losses that have been incurred by the stator. So, this is going to be equal to, let us say, some W no load. This is the no load loss of the induction motor. This will be actually equal to the mechanical losses incurred by the induction motor, because the motor is running close to synchronous speed, plus the core losses incurred by the induction motor. So, this is consisting of both these losses. We can assume that these losses are fairly constant, because the induction motor is going to run almost at a constant speed and core losses will be constant as long as I apply rated voltage at rated frequency. Okay. Now that I have the W no load with me, I can say W no load by 3 will be per phase no load loss whatever I am looking at. This should be equal to, if I look at the equivalent circuit, that is the loss that is incurred by RC. So, I should be able to write V0 square divided by RC is actually W no load loss after I subtract the stator losses, stator copper losses from the reading that I have taken. Please note, all these things have to be per phase values. If it had been a delta connected induction motor, I can say V0 whatever I read is directly line voltage as well as phase voltage. Whereas I0 whatever I am reading is line current. So, I have to divide that by root 3 to get the per phase current. So, all these values have to be per phase values. Now that I have V0 square by RC, from here RC can be determined without any difficulty. Once I determine RC, I can say V0 by RC is actually my IC, that is the core loss component of current per phase. I already have I0 with me. So, I can say I0 square minus IC square square root will give me Im, which is the magnetizing current. Now, I have Im, I have V0 with me. So, I should be able to write this as V0 divided by Im equal to Xm. So, I have got RC value, I have got Xm value, I have also got the losses which are corresponding to mechanical losses and core losses. So, I have got all that what I wanted to know, all those things from the open circuit test of a induction motor or free running test of an induction motor. So, I would be able to determine the parallel parameters. So, now I have to go on to the block rotor test to look at the series parameters of the induction motor. So, now we will start looking at the block rotor test of a 3-phase induction motor. We had seen the open circuit test of the induction motor. We have to look for the next one, which is known as blocked rotor test of 3-phase induction motor. So, as the name indicates, in this particular case, rotor will be blocked or it will not be allowed to rotate. We are going to have the rotor completely blocked. So, when the rotor is blocked, we are essentially looking at let me first of all draw the circuit diagram corresponding to this. Let us say these are A, B and C phase inputs. I am going to have a 3-phase auto transformer here. So, I am going to connect the 3 phases here like this. Now, from each of the phases through variac, so this is the auto transformer. From the variac, I am going to connect it to the 3-phase induction motor. So, let us say this is my 3-phase induction motor. Let me just show it like this, a circle, and then I am going to show the rotor here. Let me assume it is a squirrel cage induction motor. Okay. Now, I am going to connect this through, let us say, a wattmeter to one of the phases of the induction motor along with an ammeter. And second phase, again let me say I am going to connect it through a wattmeter to the second phase of the induction motor. Third phase, I am going to connect it directly. So, these are A, B and C phases of the induction motor. Now, as far as the wattmeter is concerned, let me draw the potential coil. So, the potential coil is connected like this. This is also the potential coil. For the second wattmeter, this is connected like this. Let me write this as M, L, common point, and this is the V. Let me call this as M1, this is L1, this is common 1 and this is V1. So, these are the points of the wattmeter. So, let me call this as W1 and this is W2. These are the 2 wattmeters that have been connected here. Okay. Now, this rotor is blocked. Now, what we are going to do is to increase this voltage slowly until this current reads rated current. We should not exceed rated current because we do not want to make the copper losses greater than rated copper losses, and we are going to measure the voltage across 2 lines. So, what we measure here are VSC, ISC and WSC. I call this a short circuit test because if you recall the equivalent circuit of the induction motor, this is going to be R1, this is going to be X1, this is going to be actually my XM and this is going to be RC, right, per phase equivalent circuit. Here is what I am applying as VSC, and if I look at this is VSC by root 3. In fact, if I assume this is a star connected induction motor and I am going to have essentially this as normally R2 dash by S, but S is 1. So, I can write it to be R2 dash and this is X2 dash, and rotor is already short circuited. So, isn't it very similar to the short circuit test of a transformer? That is why the block rotor test is also known as the short circuit test of the induction motor. Now, I am calling this a short circuit test, that is why I have written down these values as VSC, ISC and WSC. Now, whatever is WSC, this is the 3-phase power. So, if I want per phase quantity, I should say WSC per phase, which I may call this as W dash, this will be WSC divided by 3. Now, I can write VSC, which is the line voltage during short circuit condition. Let me get what is the phase voltage, which may be VSC divided by root 3 if it is a star connected induction motor. So, V phase is available with me, and if it is star connected, ISC will be equal to I phase. So, phase current is also available with me. So, I can say V phase I phase cos phi phase equal to WSC divided by 3, which is equal to W dash. So, these are available with me. So, I should be able to get what is cos phi ph. This will actually be the power factor under block rotor condition or short circuit condition. Now that I have the power factor, I should be able to write V phase divided by I phase equal to Z phase. that is the per phase impedance of the induction motor under short circuit condition. Now, I can say Z phase multiplied by cos phi phase, whatever I got from here, will be equal to R1 plus R2 dash. If I know R1 already, I should be able to get what is R2 dash without any difficulty. Similarly, Z phase sin phi phase will be equal to x1 plus x2 dash. I can assume that both leakage reactances are almost equal to each other. So, I can say x divided by 2 will be equal to x1, which will also be equal to x2 dash. So, block rotor test will allow me to get R1, x1, R2 dash and x2 dash, whereas the open circuit test or no load test or free running test, which we discussed earlier, will allow me to decide what is Xm and Rc. So, both these tests together will allow me to decide all these things now. So, based on this, let me try to work out one problem for the induction motor, performance characteristics. So, 3-phase induction motor, no load and block rotor test. Let me try to work out one problem. So, the problem statement goes somewhat as follows. So, I am going to have basically for open circuit test for a 3-phase induction motor, the readings are somewhat like this. It is 2200 volts, 60 hertz, 4.5 ampere, and I am essentially getting a wattage reading of 1600 watts. And when it is freely running, let us say it is running close to a speed of 1800 rpm, let us say 1760 rpm. Please understand, if I am going to have 1760 rpm and 1800 rpm will be the synchronous speed, whatever is the closest, it is a 60 hertz machine. So, 120 f by p, f is 60. So, if I say that the closest synchronous speed is 1800 rpm, then p has to be 4 poles. So, already we have deduced that the poles have to be 4 poles. Then block rotor test reading is given somewhat like this. It is having actually 270 volts as the line voltage, and I am going to have 25 ampere as the line current, and about 9000 watts is the reading. Okay. Now, what is being asked is determine Rc, Xm, R1 plus R2 dash, then X1, X2 dash. This is what is being asked. Okay. So, now let us try to work out the solution. Okay. Now, 2200 volts is given as the line voltage, and one more thing that is given is R1 is given as 2.8 ohms. This is also given. Okay. So, this is going to be the line voltage, and if it is given as Y connected induction motor. So, first of all I have to get the phase voltage. Phase voltage is going to be 2200 divided by root 3. This is going to be the phase voltage. Okay. Now, 4.5 ampere is given as the current. This has to be line current as well as phase current because it is star connected. So, first of all I should say 1600 watts minus 3 I1 square R1, which is actually 4.5 ampere is my I1. So, I should be able to say 1600 watts minus 3 multiplied by 4.5 square multiplied by R1, which is 2.8 ohm. This will give me what is the value of the losses, which can consist of actually rotational losses, because the motor is rotating very clearly, plus iron losses, right. So, iron losses and rotational losses corresponding to this, I should be able to get what is RC, right. So, for RC, let me try to write V square divided by RC will be P rotational plus P iron per phase. So, very clearly this also should be per phase voltage. So, I should say 2200 divided by root 3 divided by RC whole square divided by RC equal to 1430 divided by 3. So, from which I should be able to get what is RC without any difficulty, right. Now, I have to get what is XM. To get XM, all I need to do is, if I have V phase divided by RC, that will give me what is IC. And I can also say IC square plus IM square square root will be equal to 4.5 ampere, from which I should be able to determine what is IM. Now, I can say XM is V phase divided by IM, right. So, I have got what is the value of XM, I have also got what is the value of XC. So, when I draw the equivalent circuit, I should essentially draw R1, which is already given. I will have to find out what is X1. I have to get what is XM, which I have got exactly from this value. I have got RC, which is also from this value what I have got. Now, I have R2 dash divided by S, and I have to get X2 dash, and this is the equivalent circuit completely, which is V1. So, I am yet to get this value, I am yet to get R2 dash and X2 dash, for which I should be using the block rotor test data. So, let me try to look at the block rotor test data again. Let me write down in the next page. That was actually 9000 watts was the power, 270 volts was the voltage, and 25 ampere was the current. This is what is the data of the block rotor test. So, I can say very clearly per phase loss is equal to 3000 watts, because 9000 divided by 3. This is essentially corresponding to I1 square R1 plus I2 square R2, right. I know already R1. I am going to assume I1 is approximately equal to I2, which is actually 25 ampere. So, I should be able to get what is the value of R2. So, let me just write like this. Our voltage is 270 by root 3, which is the per phase voltage, multiplied by 25 ampere multiplied by cos phi SC equal to 3000 watts, right, from which I should be able to get clearly what is cos phi SC. Once I get cos phi SC, so this is V phase, I phase, this is cos phi SC equal to 3000 watts. Now, I should be able to get V phase divided by I phase, which will be actually equal to Z phase. Once I get Z phase, I can say Z phase multiplied by cos phi SC will be equal to R1 plus R2 dash. R1 is already given as 2.8 ohms, because of which I would be able to determine what is R2 without any difficulty, right. So, I should be able to get what is R2 dash. Now, I can say Z phase multiplied by sin phi SC, which will be x1 plus x2 dash, which let me call as x. Now, x by 2 will be equal to x1 as well as x2 dash. So, I think from this test data we should be able to get the complete equivalent circuit parameters, namely x1, R2 dash as well as x2 dash. So, we have determined all these things, right. So, you guys will complete the calculation, you should be able to do it, it should not be a problem. Let me work out one more problem on the performance of a wound rotor induction motor. So, this is about the performance of a wound rotor induction motor. Okay? The problem statement goes as follows. It is a 3-phase 420 volts 6 pole 50 hertz 100 kilowatt wound rotor induction motor. Okay. What is written is, with the rotor terminals short circuited, we are going to have the full load slip to be 0.04 and slip at maximum torque, that is S max T, which is slip at maximum torque, is given to be 0.2 when it is running at rated voltage and rated frequency. Neglect stator resistance R1 and rotational losses of the machine. Now, you are being asked to calculate what is T max, what is T starting and what is the value of full load copper loss. This is what is being asked. Okay? Now, let us try to do the solution. Okay. So, let us see, it is a 6 pole 50 hertz induction motor. So, 120 F by P is synchronous speed. This is going to be 120 multiplied by 50 divided by 6, that is 1000 RPM. So, if I want to convert this into radians per second, I should say 2 pi multiplied by 1000 divided by 60. So, which will come out to be 104.7 radians per second. So, I have the synchronous speed with me. So, this is what is omega s. Okay. Now, I should be able to write what is the full load torque. So, this is 100 kilowatt. So, TE, which is full load torque, that will be corresponding to 100 divided by omega s multiplied by 1 minus s, right. So, 100 into 10 power 3. So, this will be 100,000 divided by, this is 0.04 is full load slip. So, I can say 0.96 multiplied by 104.7. This is going to be the electromagnetic torque at full load, right. So, that can be calculated, that is not a big problem. Now, that comes out to be, I think, 994.7 Newton meter. Please verify the calculations because I have just done it quickly. Now, TE full load divided by TE max, I think we actually talked about this expression earlier. This will be 2 divided by S full load divided by S max plus S max divided by S full load, right. This expression you can derive very clearly if you have actually TE, which we write as 3 V1 square R2 dash by S divided by R1 plus R2 dash by S whole square plus X1 plus X2 dash the whole square. This is what we write for TE full load. Let us say if I am talking about this as S full load. And I can also write this as TE max equal to 3 V1 square divided by 2 omega S multiplied by X1 plus X2 dash. This is another expression. So, if you combine these two expressions, I am sure you should be able to derive this expression. Please try to derive it. This is an important expression. Okay? Now, using this, we should be able to write TE full load divided by TE max equal to 2 divided by S full load is 0.04, S max is given as 0.2 plus 0.2 divided by 0.04, right. TE full load is known, all these things are known, only thing you need to calculate is TE max. From this we can arrive at TE max equal to 2586.272 Newton meter. Please verify again this calculation as well. Now, the second division, subdivision that is being asked is what is TE starting? I can write again this expression TE starting divided by TE max equal to 2 divided by S starting divided by S max plus S max divided by S starting. S starting is 1. So, I should be able to write this as 2 divided by 1 divided by 0.2 plus 0.2. So, you can calculate definitely what is S starting, TE starting. So, TE starting comes out to be 994.72 Newton meter, which is same as that of TE full load. Is that so? Just check it. 1 by 0.2 will come out to be how much? 0.5, 5.2. So, 2 divided by 5.2 or something, that is going to be very equivalent to, very much equivalent to. So, this is 0.5, is it? So, that will be equal to 1 itself. So, that is why you are going to get essentially full load torque and the starting torque to be equal. Just verify this once again anyway. The third one that is being asked is rotor copper loss. So, rotor copper loss, how will you get it? Please remember the equation we derived, 1 is to 1 minus S is to S, that was actually PG is to P mechanical output is to rotor copper loss. So, I can say S times PG is rotor copper loss, right, at full load. This is what is being asked. So, this is 0.04 and PG is 100 is the mechanical output. So, divided by 0.96, right. So, this is going to be actually my PG value. So, this will give me what is the rotor copper loss. This comes out to be 4.176 kilowatt. Okay. So, this equation is a very, very important equation which we should remember all the time for the induction motor. Similarly, this is another important equation. Whatever is the condition at which we are talking about the slip, this is another important equation, and one more important equation which we normally talk about is this, and this is another equation corresponding to maximum torque. So, these are really important equations. So, you should actually know how to derive this, but also how to use it. Okay? So, with this we have concluded basically open circuit, short circuit test as well as couple of problems on induction mode. Okay?